Welcome back. Let us resume our discussion on the issues with the offset cancellation circuitry. We have discussed the DC bias point, non-idealities related to the switches briefly. Now, the other important issue is the closed loop response and the input interfacing. Let us look at the closed loop response, which is going to be critical as we are having the closed loop operation unity gain feedback. We would like to make sure that when the loop is being closed, the overall operation is stable, because during that operation, if the phase margin is not sufficient, it may lead to ringing. If it is falling negative, it may lead to oscillation during that period, and our purpose will be lost. So, we must make sure that you have sufficient phase margin for the closed loop operation whenever the unity gain feedback is getting connected. And then we have to see that what are the pros and cons of applying stability consideration in the closed loop. So, first we need to identify the overall closed loop circuitry that we are having for the phi 1 phase, and for that we have already this particular configuration drawn over here. This is connected to VDD by 2, we have offset voltage over here and the unity gain configuration. This is C offset. So, this is a DC point, this is a DC point. From the point of view of AC analysis, this can be seen as an AC ground. So, this is an AC ground, and then you have on the top of this DC, this V offset effectively applied at the positive terminal, and then you have the output voltage being fed back to the negative terminal, and also you have a C offset connected to the output, which is appearing between the output and the VDD by 2, which is an AC ground, right. So, I can take this C offset out and I can place it here between this point and AC ground, it has the same effect. So, from the point of view of the phi 1 phase, the C offset is effectively appearing as a load capacitance for the closed loop operation between the output and AC ground. So, because this is just a DC potential which I have applied through the switch, and this is just an AC ground, so the C offset appears between the output of the unity gain amplifier and AC ground. So, this is my load capacitance for the closed loop operation, that is the first thing. So, I can connect my C offset for the AC equivalent circuit. I am putting this to AC ground, although it is connected to VDD by 2 absolutely, and you have the C offset over here, and this point you have the V offset, and of course, in order to analyze the stability, this is again a fixed signal. If I assume that it is time invariant, it is a fixed signal. Once again, in order to apply this, check the stability, we will have to use the open loop operation and figure out what is the overall gain and make sure that the phase margin is sufficient. Now, in this case, of course, once again we have the output voltage being fed back to the input terminal in series. Therefore, at the input we have series configuration, output voltage V out is being sampled and fed back to the input. So, of course, at the output we have shunt, and the feedback factor is unity, because we are just sampling the V out, and the feedback signal to the negative terminal of the op amp is just the V out as it is. So, beta is 1. So, the overall gain A of this circuit is the open loop gain of this comparator. So, A is known. We have the AO, which we have already set around 400, that is what we discussed last day. So, AO is known, and we have the overall beta is 1. We are estimating that the C offset will be at least say around picofarad, it can be higher if we want better precision. So, based on our discussions earlier on the sampling capacitor and its analogy with the offset sampling capacitor, we are arriving at the estimation of the C offset again in the picofarad range to preserve millivolt accuracy for the sampled offset. So, this is the open loop gain, the beta and the C offset. If we do not change any of these parameters, of course, in the circuit it may be possible to change the A naught by tweaking the bias current when we are going to this phase. Suppose we are not going for those complications, we are not changing the core circuitry of this amplifier, the transistors, the biasings, dimensions, none of these are changed, and therefore, this remains A naught, the open loop gain of this amplifier remains A naught, and the C offset comes as a load capacitance. What was the role of C offset in the comparison operation? During the comparison phase, however, C offset is not coming as a load, it is just in series with the input, it is not playing any role in determining the bandwidth of the comparator. The bandwidth of the comparator will be determined by the RC time constant at the output. This is just in series, it is just adding up voltage, it is not really coming into the high frequency, it is not determining the high frequency roll off. However, in the closed loop operation, we are seeing that this C offset is appearing as an effective load, and this is the equivalent circuit. Now, remember for the overall, if I have to do the open loop analysis, again I have to open this feedback. We can apply the test signal over here and check the output over here, right. So, the open loop analysis point of view, we can apply the test signal Vt over here, and we can just put an AC ground over here, because remember this is a series connection. So, when we open this looking into the output port of the feedback network beta, which is 1, we are having a shunt connection at the output. So, we just put a ground over here, and likewise on the other side looking into the input port of the feedback network, the other is series connection, we will put a open circuit over there. So, V out we put an open circuit, and on the other side V in we put a ground, and in order to get the loop gain, all we have to do is apply the Vt and look at the V out, that is the loop gain basically. And now, if I look at the loop gain and the corresponding bandwidth that we can get for a stable operation, we know that this is a sufficiently large capacitance as compared to the parasitic capacitance. So, while discussing the comparator, we discussed that the overall pole is going to be determined mainly by the parasitic capacitance CGD and its Miller multiplication, and we did not consider a significant load capacitance present. But now we have this large load capacitance present for the closed loop scenario, and then we have to see what is the resulting gain bandwidth product. So, in our earlier example, when we looked at the open loop amplifier, open loop comparator design, we assumed that the GM1 RO1 is the gain of the first stage approximately. This is going to be equal to around say 20. So, that second stage is also similar, and overall we are getting around 400. So, suppose there was a starting point, this is equal to GM2 RO2. Suppose we have this configuration where GM1 RO1 first stage of the amplifier gain equal to second stage of amplifier gain equal to 20. So, that overall open loop gain was around 400. And also we have in the closed loop case, we know that in order to have sufficient stability, we have derived what is going to be the criteria for stabilizing the closed loop operation. The gain bandwidth product for the closed loop condition depends upon the compensation capacitor and the GM of the first stage. So, this is equal to Cc upon Gm, or in other words Cc upon Gm1, the Gm1 of the first stage. And also, in order to have 45-degree phase margin, the condition that we have discussed, this should be equal to P2, the second pole or the non-dominant pole, which is given by the load capacitance Cl divided by the Gm2, that is the Gm of the second stage. And once again, if I assume that all the channel lengths were similar and the bias currents were similar in both the stages, so the Gm1 RO1, Gm2 RO2 are going to be similar. And here, therefore, I am going to have Gm1 approximately equal to Gm2, and therefore, Cc, the compensation capacitor, approximately equal to Cl. Let us assume that Cc approximately equal to Cl for a 45-degree phase margin. So, we have the compensation capacitor given by the value around 1 picofarad, and we have the gain which is also known to us. We also need to see what is the overall bandwidth over here, which we are going to get. So, the overall bandwidth in this case for the open loop condition over here, which has the Cl and the Cc within this, within the output of the first stage and second stage. We know that the gain, the bandwidth is given by the first pole P1, the bandwidth is given by the first pole P1, which is going to be equal to Cc times the Gm2 RO2, because it gets multiplied by the gain of the second stage, times the RO1. So, this is the bandwidth of the amplifier for this open loop case. And then I also have the overall gain, which is intact, and which is given by the Gm1 RO1 times Gm2 RO2, resulting in the corresponding gain bandwidth product. Now, if you look at these numbers, we have this Gm2 RO2, which is already determined, which is having around a value of 20. So, this is close to 20, and also we have the overall P1 given by, therefore, the RO times this 20 times Cc. Now, we have to see that given this constraint, given the value of GM1, because here we are not determining GM1 from the stability constraint, the GM1 R1 came from the required gain for the open loop consideration, and for that GM RO we have this quantity anyway previously determined. Gain bandwidth product is again getting constrained because of the required Cc, and for this given GM RO and the required value of Cc, therefore, we need to see what is the bandwidth we are able to get in the overall open loop and hence the closed loop condition. So, here we have the P1 given by this product and the overall bandwidth, which is overall gain, which is given by the GM RO1 GM2 RO2 product, which is just going to be GM upon Cc. Now, based on this, we have to estimate that what is the overall gain bandwidth we are able to obtain. So, remember the overall product we are saying is anyway 400. So, we have the gain bandwidth product already given by the open loop gain, which is remaining same, we are not altering it. So, we are saying the open loop gain is remaining same, which is product of these two, which is 400, and we have the overall bandwidth over here, which is given by this quantity. So, for the overall gain bandwidth product that we are going to get is 400 divided by the Cc, which is also known, and the GM RO times RO 20 times RO, and the Cc value is also known to us. We are saying it is around 1 picofarad. So, we have around 10 to the power of minus 12 over here. Sorry? Yes, sorry. So, this is the overall gain bandwidth product that you have available from here. Also, we have the overall value of RO, which is also known, because we have GM1 RO equal to 20 from both these cases. Now, here if we look at the overall gain bandwidth product and the corresponding, say, closed loop gain. So, what is going to be the corresponding closed loop gain if we have this gain bandwidth product and the certain open loop gain over here. So, for the closed loop gain, I need to multiply this P1, which is the open loop bandwidth, with the corresponding say open loop gain 1 plus A beta, beta is 1. Therefore, in order to get, say, the bandwidth closed loop bandwidth, I will multiply P1 times 1 plus A beta, beta is anyway 1, therefore, just A times P1, and therefore, this is going to be this P1 multiplied by the overall A, which is going to be thus GM1 RO1 GM2 RO2. Therefore, the closed loop bandwidth that we are going to obtain from here, it is once again going to be just GM1 upon Cc, right. So, you have the P1 times the this is the open loop bandwidth times 1 plus A beta, where this is just A, and then A times this quantity is just going to once again give me GM1 upon Cc, which is nothing else, but I am sorry, I have just this is 1 upon Gb, GM1 upon Cc. This is nothing else but my GM gain bandwidth product. So, the closed loop bandwidth, in fact, in this case is equal to the gain bandwidth product provided by the open loop amplifier, and I have to make sure, I have to see whether this closed loop bandwidth that we are getting, which is equal to the gain bandwidth product, is sufficient, so that we can operate this closed loop operation fast enough by our clocking scheme. Now, since our gain bandwidth product we have chosen is around 400 megahertz, if you remember the discussion, this is around 400 megahertz. Our overall closed loop bandwidth that we are getting, this P1 times the 1 plus A beta, is almost equal to this, and therefore, it may not really be very significant, or may not have a serious constraint with respect to the offset cancellation loop. Now, That would imply that for the overall closed loop operation, I do not have to worry about the speed of the closed loop operation. And remember, the clock frequency that we have chosen for the overall the counter operation, this was around 250 kilohertz, and or rather this sampling period was 250 kilohertz, and we chose the clock frequency 3-4 times larger, so around 1 megahertz. And here the gain bandwidth product is sufficiently large, very large. As a result, the overall closed loop operation is not going to have serious bandwidth limitation. If you however, if you look at the CC value, however, of course, as compared to our original bandwidth that we have, if you look at the original bandwidth in the comparator, what was that equal to? The comparator bandwidth, if I just do it on a separate sheet, the comparator bandwidth, I call it bandwidth comparator, which is going to be equal to the open loop case, where the overall pole was determined by the Miller multiplied parasitic capacitance, and that I can write it as RO1, which is the RO of the first stage, times the C GD of the second stage, CGD2, times the gain of the second stage, which is A2, which is around 20. So, this was the bandwidth of the open loop comparator. In the closed loop, we are having the same RO1 almost, we have not changed any parameter. So, we have the same RO1 coming over here. Rather than the CGD2 times A2, we have the capacitor value given as CC times A2, right. So, right now we have the Miller multiplication of CC, which is much larger. So, from this point of view also we can see, if you look at the open loop bandwidth, we have RO times CC times A2. Here this value CGD, what is the value of CG2 approximately? This can be at the max say few femtofarad, few tens of femtofarad, because this is the parasitic capacitance of the PMOS input device of the next stage. Remember, how does it come into picture? The Miller multiplication is happening because of the CGD of the input PMOS device of the second stage, and there will be again few femtofarads, and this is 20, and this is few femtofarad, few I would say femtofarad. And as a result, this is this capacitance is approximately, this total capacitance is approximately going to be around 100 femtofarad. Here this value we have chosen 1 picofarad, right. So, of course, the capacitance has gone up by 10. As a result, if I am looking at the open loop bandwidth as compared to that, the open loop bandwidth of this voltage follower definitely is lower by this factor of say 100. But apart from that, we also have the overall gain, right. So, this is the open loop bandwidth given by the first pole and the Miller multiplied CC, the composition capacitor. This multiplied by the 1 plus A beta factor. Once again, if I look at it, you are having A beta is approximately equal to A, which is A1 times A2. So, you are having A1 times A2, where A2 gets cancelled, and therefore, the bandwidth closed loop, I would say bandwidth closed loop is going to be A1 times this number. So, you are going to have A1 A2 times this number. Therefore, this is having a 1 upon 100 factor as compared to this, and A1 A2 we remember around 400. So, 4-5 times larger than the original bandwidth that you had for the comparator. Therefore, in this particular case, for the chosen value of CC, we are seeing that the closed loop bandwidth may be this number is around 400, and as compared to this, we are getting 4 times the bandwidth of the comparator. So, this is the bandwidth of the let me call it bandwidth of the comparator. So, at least as per these numbers, we see that the closed loop bandwidth that we are getting for the voltage follower operation, it is higher than the original bandwidth of the comparator that we started with. And therefore, in this closed loop operation, we may not really be concerned with the settling time or the speed response of this loop. However, if suppose we go for larger C off, where we are having larger precision requirement and we are forced to use a larger C off, there of course, once we can see that the C and hence the C off becomes larger and larger as compared to the CGD, then this ratio will be deteriorating and it can go down also as compared to the present value. So, as we go on increasing the C offset requirement for larger and larger precision, it would imply that we need a larger CC, because remember the constraint CC upon GM1 equal to CL upon GM2, and that would mandate a larger value of the compensation capacitor, and hence it will reduce the closed loop bandwidth that we are getting from the compensation. So, of course, that trade off is always going to be there. Also another thing is the gain. So, if you are having higher precision requirement in the comparator, remember how did we determine the gain? That was coming from the precision requirement. In this case we have 400, but in case you are having larger gain requirement rather than 400 you are having few 1000, then of course again you will have the overall bandwidth for the closed loop operation getting limited. So, however, in this case, if we are looking for 7-bit precision, corresponding to that we are arriving at the C offset around 1 picofarad and the original gain was say 400. Based on these numbers, what we are seeing is that for our design example, the constraint is we are very much within the limit for the closed loop operation of the unity gain feedback, but this is not a generalized case, this is only for our specific case. If you have other specification, the gain of the comparator being high rather than 400 being much larger, or the offset C offset being high, that would have a different ratio, and that can make the overall closed loop bandwidth for the unity gain feedback lower than the comparator bandwidth. So, if that happens, what will be the constraint? So, if as of now it seems like we can go to our original waveform and our comparator can operate faster than this clock, that is how we have designed. So, within one clock period it can settle nicely. The closed loop bandwidth for the unity gain feedback is also even further larger. Therefore, within one clock duration it can do the offset calibration, it can store the offset value across the C offset. That is what we are concluding. So, just one clock pulse is good enough for storing the C offset, and then rest of the time can be given for the normal comparison operation, ramping and so on. As of now, that is the conclusion, because the closed loop operation, the phi 1 phase can operate even faster than the open loop comparator that we have, and within within one clock period it can complete the sampling of the offset voltage. If it so happened that the closed loop bandwidth over here felt significantly lower than the open loop, then the solution would be to either increase the bandwidth over here, or you could just apply a relatively larger number of pulses rather than doing the offset calibration only in one pulse, or rather than applying phi 1 equal to just one clock period, you go for a larger number of clock pulses for phi 1. That also of course snatches some pulses from your normal comparator operation, but rather than going and increasing the bandwidth of this comparator and burning more current, it will be more prudent probably to steal some pulses from the overall operation and apply more number of pulses over here for the phi 1 phase. So, you can see that how the circuit operation or the circuit level results can impact our control scheme, when to apply the phi 1 pulse, how many phi 1 pulses to apply, and then accordingly what is the digital control scheme. So, all these things get linked together very tightly. So, if you are messing up some circuit application, circuit implications or matrices by making this amplifier faster for the closed loop feedback, we may be dissipating more power over there, or maybe making the designs more complicated. So, rather than that, easier option will be, let us use more number of clock pulses for the phi 1 phase, so that I can even deal with the case where the closed loop bandwidth is falling lower than the actual amplifier, the actual comparator's bandwidth. Another interesting point over here that we can also discuss, this is an additional point that I would just like to mention. So far in the comparator operation also, if you remember the normal comparator operation, we have assumed that within one clock pulse it should complete the operation, and it should be sufficiently fast so that the comparator output settles within one clock pulse. If the Vref is, or if the V in the ramping Vref, for example, we go back to this plot, if the ramping Vref is crossing the Vs just at the next positive edge of the clock, the comparator should be giving the right result. But if our original comparator also has a larger delay, it is slower than the original clock, what will be the result for that? Is it going to have a drastic impact? or the impact is less serious? Can it be tackled in some other way? So, can we afford a slower comparator? In our design example, the comparator speed is not so critical because still we are dealing with 7-bit resolution, but if you go for larger and larger resolution where you have 8-bit, 10-bit, 12-bit coming in, then we can imagine what is going to be the requirement of the speed for the comparator. And in that case, can we afford to keep our comparator slower than the clock pulse? You can think about it, we can discuss this point later. What will happen if the comparator is 4 times slower than this clock? What is the result of that? Is it going to have a significant effect on the overall response, especially in our architecture when we are using 2 comparators to cater to the required input sync? What is the result if the comparator happens to be slower than this clock? What is its impact on the overall ADC characteristics? That is a nice question, you can think about it and we can discuss its implications. For that is just an aside. So, let us not digress from our discussion on the offset cancellation rule. Since we discussed about the delay of the closed loop operation of this op-amp and try to see whether it is able to perform well with the given design matrices that we have for the open loop comparator. We also briefly discuss what happens if your original comparator, open loop comparator, is slower than this clock frequency. So, we probably will discuss this issue also later. But for the time being, let us focus on the closed loop operation, and we have just seen that for the 7-bit precision and the specs that we started with for our comparator, we are in a safe position. The closed loop bandwidth is very much within a single clock or is significantly higher in fact than the clock frequency that we are using in the system. So, just single clock pulse is good enough for our offset sampling. So, summarizing, we have the closed loop operation where the C offset is appearing as a load capacitance for the closed loop operation, and there once again we need to look at the open loop and find out the open loop gain from the input to output. And there once again we have the GM-RO product determined already from the open loop comparator design. We are assuming each of them 20, and therefore the gain bandwidth product that comes as GM1 upon Cc or GM2 upon Cc. There we have the GM1, GM2, R1, R2 determined from the previous constraint. Cc and Cl are getting determined by the constraint on the sampling capacitor. We want to be sufficiently higher so that leakage and other non-idealities do not affect it. That is determining a large magnitude for the Cl and hence Cc for 45-degree phase margin. Once the Cc is known, we know the bandwidth is going to be determined by the Cc and the GM-R of the first stage. But we also have that in the closed loop ultimately we are having this 1 plus A beta factor coming in, and then we put the right number that we already have, A naught value, which is not changing for the overall amplifier. It is remaining unchanged. So, that number we already have, and based on that we are trying to estimate that what is the resulting bandwidth. So, we also looked into the bandwidth of the comparator open loop case, which was equal to or determined by the first stage primarily because there was no load capacitance. Load capacitance was very small, and we assumed that the bandwidth of the open loop comparator was being determined by the first stage differential amplifier output RO1, output resistance RO1, and the overall capacitance given by the CGD of second stage in the A, and that gives us an estimate that you are having a total capacitance 100 femtofarad. Corresponding to that, I can see what is the overall pole coming. Likewise, in the closed loop case, we are having the overall capacitance coming at the first stage only, which is equal to Cc times A2, and once again the same RO1, and we just compare these two, and we are concluding that this ratio, this is sufficiently larger, 4-5 times larger as compared to the open loop bandwidth of our original comparator, and concluding that yes, this is good enough and it is fast enough as compared to the open loop operation, and it can do the offset sampling within a single clock pulse of our ADC. And then we discuss the case whether it does go down, it goes down and becomes smaller than this, then what is the implication and how to handle that by modifying the control in the offset cancellation loop, and by applying relatively rather than just one, rather than using more number of these clock pulses for the offset cancellation. I hope this point, how did we determine the bandwidth in the comparator case, that was clear, because there what we had assumed was that there is no additional load capacitance, there is no significant load capacitance coming here, it may be just driving a CMOS inverter, therefore Cl is small, just parasitic capacitance of the gate, whereas in the second stage you are having the CGD which measures, multiplies and provides a larger load capacitance over here, and that I assume that to be the dominant pole, and hence estimated the bandwidth based on that node, and then I compared it with the closed loop. So, this is just a cross check on our assumption. Okay, so, we can take a short break and then resume our discussion on the remaining point, that is input interfacing with the offset cancellation circuitry. How are we going to apply the two input, the ramping circuit and the ramping input and the sampled input voltage to our comparator along with this offset cancellation unit. What is going to be the best way, and how are we going to place the sampling capacitor which is sampling the input data? We are going to look into that next.